chapter 4. Bismillah ar-Rahman ar-Rahim. Last time we finished that exercise and we talked about the contention-based axis. This contention-based axis category, and which includes carrier sense multiple axis and with collision detection and with collision avoidance. So we need to talk about this and as well as the controlled axis mechanism. So we have two categories of techniques. One is contention-based axis techniques in the MAC layer. We're still talking about MAC layer, of course. And in that case, we have group of nodes that share a medium. Okay. So in that case, the contention-based axis talks about the ability of these nodes to be able to send over this shared medium at any point of time, asynchronously. So at any point of time, you should be able to send. But you need to be careful before you send. You need to do something. So the best way to understand this scenario is to imagine that you have certain cars going through a shared intersection. That's exactly the same scenario, by the way. Okay. So these cars, each car, before getting into the intersection, you have to see if there is any other car in the intersection before you get in. That's exactly what happens in multi-axis contention-based techniques. And if there is any car in the roundabout, so you need to wait for a certain period of time until the roundabout is cleared. And if two cars get into the roundabout, what happens is that these two cars will very likely collide together. Okay, in which case there will be a big damage. That's exactly the scenario that happens in contention-based axis. Any node is allowed to send. However, before the node sends, the node will perform what we call carrier sense multiple axis. Okay, so each node will have to listen to the shared medium first. Okay, if there is anyone who is sending over the line, then I will feel that there is some kind of a signal on the shared medium. Then I will stop sending and I will wait for a certain period of time. Okay, so what does the node use to measure whether or not there is someone sending over the line? حد عارف? Anyone knows? What does any node use to detect that there is, or to find out, or to realize that there is a signal on the line? What do we need to do? نواف تفضل. That's what we said, but what do we need to do during the carrier sense multiple axis? What do we measure? What do we yeah. أيوة. How does it listen? How does it listen? أيوة الله ينور عليك. بس كده. That's what I want. Okay, so whenever there is a signal on the line, the energy level on the line starts to go up. Okay, so that's very important. So we measure the energy level over the line. If the energy level is, for example, like 1 millijoule or something, or 1 milliwatt يعني, per second, so we say that, okay, so there seems to be someone sending over the line. Okay, which corresponds here to the fact that we have to look with our eyes, okay, inside the roundabout to see if there is anyone in the roundabout. Okay, طيب. So when I listen, or when I measure the energy line, then I find that there is a node sending over the line. So I wait for a certain period of time, and then I have to sense again, and only if I find that the line is clear, in which case the energy level is close to zero, not exactly zero sometimes, because the noise level might make it يعني إيه, like 1 nanowatt or something like this. Anyway, so that's all good. Does that mean بقى that the carrier sense multiple axis will eliminate the possibility of collision? And if not, then how can we detect that there is a collision? حد عنده يعني إجابة ولا the quiz is occupying everyone's mind? So نواف برضو اتفضل. Uh-huh. Mm-hmm. How do we detect that there is collision, نواف? Mm-hmm. Yeah, ازاي how do we detect that there is collision? يوسف اتفضل. خلي يوسف برضه. How do we detect that there is collision? يعني احنا we agree now that carrier sense multiple axis does not eliminate collision. Okay? أولا, how it does not eliminate collision, and if the collision happens, how can we detect it? We talked about this. ناصر اتفضل. ايوه, how لا. بص, هو شوف, you need to be accurate. يعني if you have watched the video clearly, you would know the answer right away. So carrier sense multiple axis is used only to detect whether there is a transmission over the line or not. Okay, it does not eliminate collision. Why? Because if two nodes listen at the same time to the channel, both of them, they will find that the channel is empty. So both of them, they will try to send at the same time, and the collision will still happen. So just the fact that we're doing carrier sensing, it doesn't mean that we eliminate collision. Okay, we cannot eliminate collision for contention-based access techniques at all. Okay, so we cannot eliminate it. We can reduce it by doing carrier sensing. Carrier sensing will reduce it, but will not eliminate it. So now, when the collision happens, how can we detect it? We detect it actually because we said that if one node sends, let's say the energy level on the line will be like 1 milliwatt or something. If more than two send over the line, the energy level will actually be 2 or 3 milliwatt. Okay, so we know that there are more than one node sending over the line. That's possible under one condition, that the medium is guided. Guided medium means that the energy goes into a copper line, or it goes into a line, like even fiber optics. So UTP, STP, coaxial fiber optics, all of them are under the category of guided media. Okay, it turns out for guided media, the energy goes into a straight line, okay, and it does not lose its value, it does not lose its strength easily, okay, which means that if I measure the energy line, or the energy level here, and it's 2 milliwatt مثلا, chances are here it will be 2 milliwatt, here it will be 2 milliwatt, here it will be 2 milliwatt. Okay, so if it will be around 2 milliwatt across the entire cable, because it's a guided medium and the energy is going into a straight line. طيب, so now بقى, when we have guided media, we can detect the collision. That's good. So what about wireless? Wireless is not a guided medium. So for wireless, we have nodes like this, okay, and these nodes, when they send, there is like some kind of a signal that travels through the air. Unfortunately, when this signal travels through the air is not a guided medium. So the air makes the power line here, the power level here and here and here and here, all of them will be different. Okay, so we cannot really rely on measuring the energy level at different locations in wireless, because this will not be accurate. So in other words, we cannot detect a collision. So for wireless, we cannot detect a collision. We can do carrier sensing to some extent. Even the carrier sensing will not be absolutely accurate, but we can still do carrier sensing. But we cannot detect the collision. That's why for wireless, we have to use another technique, not collision detection. We have to use collision avoidance, because we cannot detect the collision. We try to avoid it. And this is for the case of wireless or unguided media. So for unguided media, we have to do collision avoidance because we cannot detect the collision. That's very important. Okay, so collision avoidance through what? Through multiple ways that we do not have to go through it. In network 2, you will have to learn all the details about these collision avoidance techniques. Okay, so we don't have to go through the details of this. Type, that's all good. So we have carrier sense multiple access with collision detection. Carrier sense multiple access does not eliminate collision, but if the collision happens, we can detect it. And this is good, because if I can detect the collision, okay, then I stop right away and I don't have to continue even transmitting anything, because currently there is an accident in the roundabout. So I have to wait until the accident is cleared and then I try again. Okay, so that's good. If I cannot detect the collision, that's not very good, because then the only way for me to know that there is a collision is that I have to wait for a very, very, very long time, because I sent I sent a particular frame and I did not receive any acknowledgement, anything. So I wait maybe for 100 or 200 milliseconds, and I did not receive any acknowledgement. So then and only then I say, okay, so there have been a problem. Then I have to retransmit the frame again. And that's why in wireless, the delay is higher, because you cannot detect collision. Type. So the question now is, can I actually eliminate the collision altogether? So the answer is yes, and that's through what we call a controlled access techniques. In controlled access techniques, I can actually eliminate the collision altogether. And the only way that you can eliminate the collision altogether, so let's imagine that we are in a meeting, okay? We are in a meeting and we are coming to the meeting that we know the meeting will be arranged in such a way that I will divide the time of the meeting into slots, or for that, using the channel terms, or using some frequency. Either we divide the channel in the time domain or in the frequency domain. And I would say, okay, so this slot will be assigned to Amr. This slot will be assigned to Muhammad. This slot will be assigned to Ali, and so on. Okay, so the slot of Amr, if Amr has any data to send, Amr will send. And while Amr is sending, everybody is abstaining from transmission, because they know that this slot is assigned for Amr, so they cannot use it. Okay, nobody can speak during the meeting in the slot of somebody else. So in that case, everything is controlled. Everything is controlled. And in that case, we eliminate the collision altogether. So we divide the shared medium into time slots or into frequency ranges. Because as we said, this line or this medium has certain frequency properties or certain bandwidth. Okay, so we can divide this into frequency ranges and have Amr again. Amr will send here, Muhammad will send here, and so on. So each one sends in a small frequency range, okay, and they can use filtering and so on. Again, the details about this you will learn in network 2. طيب, so that's one way of doing controlled access. Another way which is a little bit deprecated, it's obsolete, which is what we call, so this is we call this TDMA, or FDMA. So time division multiple access or frequency division multiple access. Number two, under the controlled access techniques, we call it token ring. Token ring here is a little bit deprecated. And to understand token ring, let's imagine again that we are in a meeting and there is a mic, okay? So we have sort of a mic in the meeting, and this mic goes into a circle with a certain sequence, okay? So it goes first to me, then I say, okay, do I have anything to send? If I have anything to send, I will hold the mic and then I will start speaking. While I'm speaking and I have the mic, I have the access to the shared medium and nobody else has access to that mic except me. So I know that nobody else can send because nobody else can speak because I'm the only one who has the mic, okay? And then if I don't have anything to say, then I pass the mic to the one next to me, okay? If Muhammad has nothing to say, then he passes the mic right away. So this is what we call a token ring. So it's like a ring and everybody is connected to it, okay? And there is a token. A token in data networks is some kind of a small control frame that goes, this is a mic, yani, that goes into a sequence. It goes like this, okay? If anyone has any data to send, they will hold that token and they will start transmitting. So only the one who holds the token is allowed to transmit over the medium. So again, this way we eliminate collision altogether because the only one who's allowed to send is the one who has the token, and it's only one at a time, okay? So that's the control access. In controlled access, we eliminate collision altogether. We don't have to detect collision because it does not happen, which is all good. But the problem is that for TDMA, for example, if Amr does not have any data to send, then this time is wasted because this is only assigned to Amr. So this is not to say that controlled access is always better than contention-based access. We cannot say that. So it depends on so many factors. That's why both of them, both the controlled access and contention-based access, are used in data networks almost equally. Because depending on the application, you might want to use controlled access or you might want to use contention-based access, okay? So this is not to say that the performance of one is better than the other all the time. Type. All right, so that's good. So these techniques, contention-based access and control-based access, are for multi-access, where you have multiple nodes sharing the same medium. Now, there are different class of access methods, which is what we call a point-to-point. In point-to-point, we have only two nodes like this, node 1, node 2, and we have only one medium between them. So there is no multiple access here. There is no, not so many nodes are sharing one medium. It's only two nodes. They are connected point to point. There could be some small network here or some switches in the middle. There's no problem. But at the end, you have a point-to-point connection. So for this point-to-point connection, there are different properties because here there's no collision, obviously. Okay, so the nodes, node 1 and node 2, they don't even have to specify a specific address. Remember, in multi-access, because I have multiple nodes connected on the shared medium, I have to specify the address of the one that I want to communicate with, right? Because I have plenty of them. In point-to-point, I don't have to specify an address. Anything I will send from 1, it will go to 2. Anything I will send from 2, it will go to 1. Okay, so you don't have many choices here. So number one here, no address. Okay, because we said in multi-access, it's like a house, and I have to specify the name of the person that this data should go to. In point-to-point, I have only, I'm Amr and I have Muhammad. So anything I will send, it will go to Muhammad. Anything Muhammad will send, it will go to me. Okay, so there is no need for addressing here. So the only thing that we need to control in point-to-point is the fact that if this line is what we call half duplex, in half duplex, we will divide the same. It's like one-way street. It's like one street كده. Okay. So there is one street between me and between 1 and 2. Okay. So either this street will be used for 1 to send to 2 or for 2 to send to 1. So the only way I can do that is again by dividing this line into 2 time slots only. 2 time slots. One time slot for 1 to send to 2, the other time slot for 2 to send to 1. It's the same street, but it has to be used in each direction at a time. Okay. We don't have, by the way, we don't have these kind of roads in Qatar, but they exist in Canada and North America. It's like one street, the same street, for a duration of time during the day, it will be in one direction, and then it switches the direction on the other way during other times of the day. So that's what we mean by half duplex. For بقى full duplex, there is full duplex, and in that case, 1 can send to 2 and 2 can send to 1 at the same time. And the only way that this could happen is by dividing the line into in the frequency بقى, not in the time. So 1 can send to 2 in a frequency range, and 2 can send to 1 in another frequency range. And this is exactly what we have on the roads. Roads are divided into 2 directions. Okay, are divided into 2 parts. One part will go this way, and one part will go this way, and they both concurrent. Okay, so there are certain cars going in one direction, and other cars are going in the other direction. So it's a two-way street. Okay. So that's for point-to-point. So very quickly, we want to talk about the Ethernet frame structure. And remember, we talked before about the generic frame structure. We talked about the generic frame structure, right? And this is part of the reference model, the ISO reference model. And we said that this is abstract and it does not align with any specific protocol on the internet. Now, this is the Ethernet frame structure, which is defined in the TCP/IP protocol model, which aligns with a specific standard, which in that case is Ethernet. Okay. So this is the frame structure. We will find very high similarity with the generic frame structure that we talked about before, but there are some differences. So very quickly here. So what is the So here, matching these boxes in the spaces here, what is the first one? What comes here in the beginning of that frame? نواف تفضل. Preamble. Okay. Then after this, the address. Bravo. And the address here, we have we have 2 addresses. We have destination and we have source. Which one comes first? Destination. We talked about why actually. I will talk about this in a minute. And then source, صح. And then ما فيش بقى. We don't have protocol here. We have type, which is the protocol. صح. كلامك صح. هو type indicates the protocol. And then the data, of course. And then the frame check sequence. تمام يا نواف. تمام. So the preamble, we talked about a different in the generic data structure. We talked about a different field here. Do you remember? كان اسمه ايه؟ اسمه start frame. Remember كان عندنا start frame وكان عندنا هنا stop frame. ماشي؟ Now for Ethernet ما اسموش بقى start frame، اسمه preamble. ليه بقى؟ الpreamble ده it has 2 functions, not just start frame. Start frame is one, and number 2, it has some functionality to provide synchronization. So the preamble is actually divided into 2. Here we have 8 bytes. Okay, so these 8 bytes are divided into 2 parts. one part is to provide the start frame, which is what we talked about before. So we need to mark the beginning of the frame. We talked about that. And the other one is synchronization. ليه بقى synchronization? Because here, remember, Ethernet is again for multi-axis. Okay, so these nodes, they have to really synchronize between each other to try to mark the beginning and the end. They need to synchronize their clocks very accurately. Okay, and remember, we talked in Manchester encoding, we talked about Manchester encoding having self-synchronization. So Manchester encoding will help here. However, we also need in the frame some synchronization bits to make the synchronization really, really accurate. Because here we're talking about multiple nodes trying to access the same shared medium. So they need to have some means of synchronization. So that's preamble. Destination. In the destination here, we said that the destination comes first. Why? Because again, the MAC layer is actually designed in hardware, and in hardware we read the frame in sequence. It's not a data structure in the memory that we can read any part of it at any point of time. In hardware, we need to read these frame fields in sequence. So switch, for example, he stops here. The switch stops once it reads the destination address, it stops, and then it performs its function and it goes outside the picture. Okay, so that's why we need the destination first. The type indicates the protocol, as Nawaf said, and the protocol in the higher layer, in the network layer. Okay, the data part, of course, we need the source address. In case there is an error, I need to report it back to the source. So we always need the source, as we said before, so that if there is any error, I need to report it back to the source. The data part, this is actual data, and we notice here that the data ranges from 46 to 1500. Again, there is a reason for this that you may actually study in Network 2. Why 46? Why 1500? So there is a reason for this. Frame check sequence. The frame check sequence here is what we use for error detection. We detect error, any error that happens in the data, because this data at the end of the day travels as an analog signal over the line, and analog signals, they suffer from some noise. So this noise may cause the data to be corrupted, in which case I need to detect it. And what we use here in terms of technique for frame check sequence is what we call cyclic redundancy codes. Cyclic redundancy codes, and these codes, they are combination of these data to try to make sure that whatever modification happens in the data, I can detect that there is some corruption in the data, so I stop. So this is the frame structure. We'll talk about this again على فكرة in chapter 5. So that's why I'm going a little bit fast, because we will talk about it again in chapter 5. طيب. So this is not for point-to-point. For point-to-point, unlike multi-axis, for point-to-point, we have only two nodes involved in the transmission. So we have node 1 and node 2. And as we said, so here we don't need to have address per se, okay? Because anything that gets sent from 1, it will reach 2. Anything that gets sent from 2, it will reach 1, okay? So we don't need to have address per se, but we still have address here. So first, the first byte here, the first byte is what we call the flag. And it's only one byte. Why? Because this is actually, flag is a frame start. And we don't need to have very sophisticated synchronization here. We don't need to have synchronization here. Because again, it's point to point. It's not multi-axis, so we don't need any sophisticated synchronization in that case. We have address here, which is a little bit strange, because I told you there should be no address, but the address field here is fixed. Is actually fixed. It is in hexadecimal. It's always FF. Okay, it's always FF. FF here indicates when we have an address field that's all ones, that always indicates that this is broadcast. Okay, this is always broadcast. Broadcast means that I don't have to send it to a specific node. I can just send it to whatever node on the other hand side. Okay, طيب. So the address exists, but it's fixed. And the reason that we have this address field is because there is 1% of the time the value of that address is not FF actually. But again, this is the exception. But in point to point, we don't really need to have address field, but we have it in the frame to indicate some control signals that we don't have to go through. Okay. Then we have the control. We have the control field, and control field is used again for two things: for flow control and reliable communication. Okay, flow control, reliable communication. ماشي كده? We talked about that before. Then the protocol, which is the type, it's the same. Protocol or type, it's the same. And then data, and then frame check sequence. Same thing. ماشي كده يا شباب؟ So in point to point, it's a little bit different because we don't have multi-axis. We don't have high probability of collision in that case. So we can easily organize that point-to-point link to work as full duplex or half duplex. It's much easier than multi-axis where I have multiple nodes sharing the same medium, in which case I need to specify the address. I need to have very high sophisticated synchronization. Okay, and I need to resolve the collision in case it happens and so on. Okay, any questions? Any questions يا شباب? In chapter 5, by the way, we will talk about, in chapter 5 we will talk about Ethernet again. Chapter 5 covers Ethernet in a lot more details. So if there is any thing that went fast and you were not able to capture 100%, we will talk about it again in chapter 5 inshallah. Okay. Okay. By the end of today inshallah.